science's prediction and the discovery. Albert Einstein put a theory together called the theory of relativity. And it wasn't until 15 years later that he was proven correct. He was proven with this image right here, an eclipse. So imaging in science is one of our main focuses. This is what we need to do, is be able to see and image things in order to understand them fully. So what if light was a little bit different than it is back in that Einstein had experienced, and the objects that we were looking at actually reflected light or absorbed it in such a way that we didn't see it visually with our eyes. An object at a distance would look pretty much like this. You'd see part of it, not very clear, be able to not to detect any relative distinguishable images out of it. If we got a little bit closer to it, we'd actually see that we could see some shape, but a part of it would also be absorbed in there, and we wouldn't have a very clear image of it. And if we get a little bit closer, we'd actually see that those large blocks of areas have broken down into discrete, small images. And we're able to see kind of a boundary condition that's there. And we're able to distinguish a little bit in between there about what's going on. So if we get a little bit closer to it at 100%, we actually can tell that this is Van Gogh's Starry Night. And that's our objective, is to image things as fully as possible. One of the best examples I can find of this is that in 1994, a gentleman named Nicholas Clapp convinced NASA to turn on its ground-penetrating radar that was in the space shuttle and image part of the Arabian Peninsula in the region of Dhofar in Oman. What he was looking for was a road that was told to him that existed, that went to the lost city of Ubar, that was called the Atlantis of the Sands by Lawrence of Arabia. So he was in search of this. He convinced NASA to turn on, and what they found was a series of roads that had all congregated into this one area. So he knew from that, from his imaging, that that was most likely the area he needed to go to. So when he got there, he did find a city that resembled the Ubar in the legends. And excavations later on in that area led to the understanding that there was a fortress there, and it had been in existence for a long period of time, dating back to at least 300 to 500 BC. And it was part of the frankincense trade that was used back then. We also discovered that in there that a large sinkhole had occurred and wiped out a large section of it, leaving the inhabitants nowhere to go. So I think this is the first occurrence of a sinkhole actually causing this catastrophic damages to a human structure. So sinkholes in Florida. Why are we concerned with those? Basically, we see these in the news almost every year. You'll see occurrence of them. Each one of us, I think, who live here in Florida and are a homeowner actually thinks that at some point in time that it's possible that a sinkhole could be occurring if it happens. So catastrophic events do occur. And our understanding of those things sometimes are not really all that clear. Citizens did a study to find out how many claims are represented by sinkholes. And what they came up with is between 2006 and 2010, almost 24,000 sinkhole claims were filed in the state of Florida. Now these were all congregated in what the news agency calls Sinkhole Alley, which is Hillsborough County, Pasco, Hernando, Pinellas County. So it's all kind of grouped into one little area. So why are we interested in this? Well, sinkholes do cause a lot of damage, and they're a threat to us, particularly for the infrastructure items. So what do we need to do? Well, from this image here, you can see that there's a dotted line at the top, and that's usually where most of our surface imaging gets us to. Basically, right to the top. You see a little circle right in there. That's where we need to be. The sinkholes start forming in the limestone and the material starts moving downward, because that's where it all begins. So we need to be able to understand that fully. But our technology really hasn't given us there. So, how do we know if we're testing in the right locations? Most of the time, we send drill rigs out, and these are tested, and it's a random event. So, we like to be able to refine them. We like to be able to see down there and say, you know, this is precisely the location we need to get to, precisely what we need to do. So about 8 years ago, I took a course at the University of South Florida involving geophysics, and when I was exposed to the mathematics of geophysics, I came across the idea that the electrical resistivity for the mathematics, it started at a single point underground, with electricity flowing in a sphere, pretty much like this object right over here. So I understood that you could inject current at that point in time and recover the data. The normal method was to work out the mathematics and get it to the surface. So we came up with the idea of putting an implant into the ground and injecting current near our target, to be able to see what we're see down to the depths where the sinkhole formations are starting to occur. And we stood that here in an area in Hillsborough County near the University of South Florida. We have two test sites, one actually on the University of South Florida, another one at an apartment building. It's called the Bordeaux Apartments, adjacent to it, just east of it. Now we also incorporated Dr. Sarah Cruz, Anna Kofu, a PhD student, M.H. Loki, a PhD in Malaysia, and another gentleman called Dr. Wilkinson in England to assist us as we went on the testing of this. So the first case study that we did was at the Bordeaux Apartments. That in 2010 had swallowed a car. It's a Toyota Camry. It's about 15 feet long. So as you can see in the images here, it slowly disappeared completely. It was right adjacent to the building, so it was certainly a primary concern to the property owners. So we got involved in this. We went out there to do some work. As you can see in here, the geophysical line where the arrow is showing is right across the area. The area of the sinkhole is where the asphalt is. And surprisingly, nobody parks there. So, it's a bust. So we began putting the implants in and seeing what we could use. The images that we got from this were these two images. One we conducted with a standard surface electrical resistivity method, and another one with our method. As you can see here, these look quite different. As you can see clearly, here there's a line drawn across this image right here is about where that top image stops. Top image, I believe, was about 8 meters or 24 to 26 feet. This image here was taken, I believe, at 20 some odd meters or 60 some feet. Very similar to that. So this is a geologic interpretation of what we have here. The yellow area at the top is the sands. The area between there is the clays. The orange area depicts the limestones. You can kind of see there's sort of a conduit system right off here to the left-hand side. And you can see by the circle right in there that that's the location of the car. So I think we're the only people that have actually imaged a car in a sinkhole. Not that we'll use that a lot, but hopefully not. So now at USF, our test site there, you can see the arrow. This is the location in the center of the sinkhole. There's approximately a 3-foot drop from the point that you're seeing right here down to that point. It's almost about 130 feet in diameter. So the images that we took there, you can see our image. At the top is our merit image, and down below you can see the electrical resistivity image and a ground penetrating radar image that was done by Dr. Sarah Cruz at the University of South Florida. What we can note here is that the ground penetrating radar image is approximately 3 meters. This is, again, at about 8 meters. And the capability, the resolution of this is very, very low. We can detect some things, but not a lot of these. The image that we did with Merritt at the surface, at the top up there, as you can see, there's a surface of limestone that can clearly be seen, and therefore the definition of the geometry of the sinkhole can be identified. This is the geologic interpretation of that, where we can kind of see where it all slopes down into one centralized area where there's most possibly a conduit system extending even further down than that. So we can kind of really get an idea of what's going on down there. Well, previously, it was pretty much guesswork. And the instrumentation that we were using wasn't really getting us to that point. In addition to the standard method that we did, we developed a unique concept called an offset method, where we take the surface electrodes and spread them out. This provides us with a quasi-3D image of the sinkholes. You can kind of see the various images on each side of that are related to the planes that are created by moving the surface electrodes over. So we can kind of, in a cheap, effective way, basically, get kind of a three-dimensional view of this. So how do we know if we're doing this right? Well, what scientists use is what's called a sensitivity method. The data that we have is pumped into an equation. Those equations then generate an image much like this. As you can kind of see from the highly colored area on the left-hand side here, that data is very intense compared to the image on the right-hand side. The image on the right represents about 250 data points, while the image on the left represents 650 data points. So we've increased the depth, we've increased the amount of data points, we've increased the resolution. So in addition, what do we do after we find a sinkhole? A lot of times we want to find out what's going on. Is it a danger to us? Is it not a danger? One of those techniques would be what we call time domain reflectometry, in which we can send a signal down the cables in a unique method for the same implants that we put in, and these can monitor whether or not ground movement occurs. So we get two things out of the same process. It's much more cost effective that way, and our assurance of what's going on is much higher. So this is kind of what it would look like for a sinkhole image. That area would be affected that you would expect it would come to the surface, and how a monitoring device would work in there as well. So why do we do this? Basically, sinkholes do represent a threat to infrastructure, our homes, and even life to an extent. What we need to do is be able to get down to that particular areas in order to predict and discover what's going on down there, and to fully understand how to remediate and take care of these things before they become a problem. To date, what we do is the problem ensues, and we come out and define what it is. But if we were to predict what's going on, we need better tooling for that. And this is one of the ones that we present. Thank you very much.